Hi, this is Mr. Conti, and today we're going to cover advanced applications of derivatives. These are normally topics that are taught at the college level. They're certainly important in both the areas of mathematics, but physics and engineering as well. And those are series, but we're going to delve into talking about a specific type of series. But just as a brief introduction, a series. An example of a series is what you see here at this first example, where we have in sigma notation, the summation notation here, the sum of some quantity n from n equal to 1 to n equal to 4. That forms what we call a series, because what we'll do is we'll take and input the value n equals to 1, and then we're going to add to it the terms that take us from n equal to 1 to n equal to 4. So that's just 1 plus 2 plus 3 plus 4, and you get that the total sum is equal to 0. A specific type of series is called the power series. That's where we actually use n, the index n, as an exponent, and that's going to create us a series of powers of x. So if we also run the series from n equal to 1 to 4, but we then use x to the power n, then you'll get 4 terms in this series, all of which have base of x but have exponents that increase by 1 in each term. But what I like to go over with you guys today is something called the Maclaurin Series, which makes use of derivatives that we've recently learned, and more importantly, the Maclaurin Series has the ability to take some weird functions like the trig functions or the exponential and turn them into a power series of polynomials, which in many different applications are much more useful and convenient to work with. So again, I'll be going through some things pretty quickly because I want to just give you a basic overview. So without deriving what how the Maclaurin series came about, I'm just going to tell you how to find the Maclaurin series for a given function. So let's just take a function f at x. To find its Maclaurin series, we have to so basically you're going to get a series of powers of x that increase, and in order to shape the polynomial just right to match the function that you are going to try to emulate, you need specific coefficients, and so the coefficients are derived based on derivatives. So that's where the application of derivatives will come in. So the first term of the Maclaurin series is the value of the function evaluated at 0. I should say that the Maclaurin series, because there's a series that is a bit broader and can cover any function around any specific spot. But what we're going to be looking at, the Maclaurin series specifically looks at trying to imitate the function around 0. So that's the important place. But other series are more generalized, that you can have it imitate a function at some other location rather than 0. But let's start with f at 0. The second term of the series is f prime at 0. So you'd have to take the derivative of your function f and then plug in 0 in for x, and that'll give you a number. And then we get our first power of x here, x to the 1. Here you can kind of imagine that this is x to the 0, but we don't have to write that down. The next term is f double prime. So with each increasing power of x in the series, you're going to get an increasing derivative. So in order to find this coefficient, you'll have to find the second derivative of f and then plug in 0 in for x, and you'll get a number. You'll have x squared is the next power, but now to accompany these terms, you're going to get a new term, which is 2 factorial. These are present here. This is the 0th term. So 0 factorial is by definition equal to 1. and 1 factorial is equal to 1 as well. So you have a 0 factorial and you have a 1 factorial here that aren't explicitly written. So this is going to be the pattern from here on out. You would expect, if you were to predict what the next term of the series would look like, you're going to have a third derivative with evaluated at 0, x cubed, and then you're going to have a 3 factorial. Now that's going to continue on to infinity. So it's only going to equal the function if you allow it to go all the way to infinity. If you stop at any point along the way, you'll get a good approximation. The more terms you add to the series, the better the approximation. But it's just going to be approximation unless you go all the way out into infinity. But theoretically, if you make it go all the way out into infinity, there are proofs out there that will show that it will equal the function exactly. Alright, so there's a way that we can simplify this down a little bit. So we'll use the sigma notation. So let's just think about this real quickly. So we're going to take, we have a 0th term, so I'm going to take my index n, and we're going to go from 0, and we have to carry that all the way out into infinity. And we have 3 basic parts. We have derivatives evaluated at 0. So we can write that we have fn at 0. So this n is the derivative. So on the 0th term, that means you don't take a derivative and you just evaluate the function at 0. If it's f prime at 0, that means you take the first derivative. If you go to the second term, n2, that's the second derivative. So that covers that piece. You have the factorial. So it's n factorial. And then you have x to the power n. And so that's the shorthand for the Maclaurin series. This is just a short way of writing this whole series. So let's actually do a couple examples. So we're actually going to figure out the exponential, and then we'll figure out sine and cosine. The exponential is the easiest one to do because the derivatives are really easy to find, because it's the same. So here's our f at x is e to the x. So if I would say let's find the Maclaurin series, we need to find all the derivatives so that we can evaluate the derivatives at 0. So let's see what we get. Just take a couple derivatives to start. So f prime at x equals e to the x. The derivative of e to the x is e to the x. F double prime at x is e to the x. So don't have to take it further than that. I can tell that the derivatives are all going to be the same. So then we're also now going to evaluate the function at 0. So we have e to the 0 is 1. And guess what? It's going to be the same thing the whole time. So every time these terms come up in the series, we just plug in 1. So what's left over? Well, it shows that e to the x written as a Maclaurin series is equal to f at 0, which is 1, plus f prime at 0, which is 1, times x, plus f prime at double prime at 0, which is 1, x squared over 2 factorial, and so on. So let's write that down. So we have 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and at that point you get the drift. That is e to the x. So if you go all the way out to infinity, you will have a new way of expressing the exponential function. We could turn this into a using sigma notation to make this more condensed. So we want to go from n equal to 0 to infinity, and we don't have to worry about the derivative terms because they're all equal to 1. So all we need is just to have the x to the power n and then our n factorial. So again, I plug in 0, I get n to x to the 0 over 0 factorial is 1, x to the 1 over 1 factorial is x squared over 2 factorial, x squared over 2 factorial, and so we get that simplification. So I want to show you, I'm going to take you guys to Desmos, and let's see what I have selected here. I've got a couple of things already lined up for you. Here we have, I typed in the what we just wrote as our exponential. This slider allows me to add terms of the summation of the series from 0 to 100 if I want to. So right now it's set equal to 0. So if I tap this, the 0th term is 1, so that's why it's just giving me the value 1 there. But let's see what the actual exponential looks like, the exponential function. So it's obviously a horrible approximation, except for the fact right at 0, that is a exact approximation. I guess that doesn't make total sense. It's exact. It's not an approximation because it's equal to 1 at x equals 0. So that's the only place that it's good. Everywhere else it's a really bad approximation. But we have to keep adding terms. So let's creep this up by 1 increment and see what happens. Now we're at a equals 1. That means we have 2 terms in the series. That's 1 plus x. Well, you look at what we got here. This is basically almost like a tangent line that touches x only at that point. And suddenly, in the local vicinity of x equals 0, you get a pretty decent approximation. But still, you know, over a wider interval, it's still pretty bad. But let's keep going. We're going to get a quadratic now. And you can already start to see, here's the x squared term. And it's looking pretty good around here. It starts to deviate. But the idea is it becomes exact if you add all the way up to infinity. But it won't take us long on this scale for us to see that we can get a good approximation of the exponential by just adding a few terms in the series. So if I add 15 terms in the series, you cannot tell the two graphs apart. If I were to zoom out, you would definitely be able to. But in this scale, it is an exact, it looks, there's no distinction between them. Now, let me just change this up a little bit. So what I want to do now, I'm going to bring this back to 0. We could use this Maclaurin series to actually approximate the value of E. And it's actually how they do it. The Euler's numbers. So what I would need to do to get the value E, I go into here and I type in, I want x equal 1, right? So that's just E. So there's 2.71828 and so on. So that's the value E to that many sig figs. Well, to do the same thing, I come up here and I plug in for x 1, and now we're going to compare these two numbers. So if I just have the 0th term of the series, that's 1 to the 0 over 0 factorial, that's 1. And again, we said that that's not going to be a good approximation of the series. But let's watch what happens. I add one more term. You get 2. Well, we got the first number right now. Add 2 terms. 2.5, getting closer. 3 terms. If you round to 2 sig figs, 2.7, 2.7, that's pretty close. Let's add 4. There's the 2.7. 2.71, and we're just going to keep on going here. And by the time I get to 13 terms, look at how many numbers agree. You have to come all the way out to this last digit where you see a 5 and a 6 that are different. Once I cross that boundary, you cannot tell the difference. You get a good approximation for E to that many places. And it only gets better from there, given that you keep adding the terms. But it's only as exactly equal to E at infinity. So that's the difference. All right, we're going to do sine next. Sine of x. So f at x equals sine of x, and we're going to take some derivatives, evaluate the derivatives at 0, and build our series. So derivative of sine of x, cosine of x. Take the second derivative, so the derivative of cosine minus sine of x. Third derivative. What's the derivative of negative sine? Well, the derivative of sine is cosine, so I'm just going to bring the negative along for the ride. Now, once we get to the fourth derivative, it's not proper usually to keep writing these primes. I'm going to put a 4 there. So it's the fourth derivative of sine. Well, the derivative of cosine is minus sine, but there's already a minus sign out front. So the minuses cancel, and guess what? We get sine again. So it took us 4 derivatives to repeat, and we expect then that pattern to continue now. So it'll be fifth derivative is cosine, sixth derivative is negative sine, and so on. Now we evaluate them at 0, which are pretty straightforward numbers. So sine of 0 is 0. Cosine of 0 is 1. Negative sine of 0 is still 0. Negative cosine of 0 is negative 1. And then we repeat. So an interesting pattern that develops here is that every time we have signs in there, we get 0. The cosine terms give us a value, but they alternate in sign. Sometimes it's 1, sometimes it's negative 1. So to find some pattern, we just need to write this out. So let's just write sine of x. So in the Maclaurin series, we're going to first pull out f at 0, which is 0. So there is no 0th term of the Maclaurin series for sine of x. So really, if you're thinking in terms of the summation notation, we can start with n equals 1, because now n equals 1 will give us an x. So we have 1 times x, which is just x. And this is actually the small angle approximation right here. If I just stop it right there for a second, this is called the small angle approximation. So with small angles, you get a pretty good approximation by setting, and this is in radians. If you plug in sine of some angle, it'll generally equal that value in radians very closely. As long as usually the approximation is good within maybe about 5 to 10 degrees. So for low oscillations, we usually use this approximation. But you build up more error the larger the angle is. But let's just continue on. So just this piece is considered the small angle approximation. Actually, I'll just keep that as its separate own thing and start to write the rest of the series. So now the next term, which is the n equals 2 term, would require this 0 here. So I'm not going to have to write that. So I move on to the n equals 3 term. Well, I get a minus sign, and then I get x cubed over 3 factorial, and that's the rest of the stuff that comes along. No fourth term, no n equals 4 term, so we're going to n equals 5, but that's when it repeats. So n equals 5, we're going to get a positive 1, x to the 5th over 5 factorial, and you can now start to guess what these next terms are going to be. So it's going to be a minus x to the 7th over 7 factorial plus dot dot dot, and it'll keep going. So I'll show you an interesting way of rewriting this in summation notation. This is not obvious, but once you see it, it's something, tricks that mathematicians and even physicists will use a lot. So like I said, we only need to go from n equals 1 to infinity. We don't have to include that 0th term. So we have a couple issues. First of all, we only need odd powers of x, 1, 3, 5, 7. So the way you represent odd numbers is in the series with these indices is you go x, and then the exponent is going to be, you take 2, multiply it by n, and subtract 1. And that sometimes depends on where you start, but with n equals 1, let's try it out. If I do x to the, I plug in n equals 1, I get 2 times 1 is 2 minus 1 is 1, and that'll get me this x term. If I go to the next term of the series 2 times 2 is 4 minus 1 is 3. I get x cubed. That'll get me this term. So that works. And since the power and the factorial are equal, then you'll just rewrite the same little trick here at the bottom. So you'll always get these, the number of the exponent and the factorial will always agree. But the only other complication here is that you have alternate signs. You get a plus, minus, plus, minus. So typically what you do is you take a negative 1 out front of here, and you raise it to a power where every time so you can get the negative 1 to alternate, because if you raise it to an even power you get positive 1, but you raise it to an odd power you get negative 1. So let's just see, if I raise it to the power n by itself, and I plug in 1, I get negative 1 to the 1, that's negative 1. That would put a negative out here. That's not what we want. So let's just shift it by 1. So I'll raise it to the n minus 1. So now if I plug in 1, I get 1 minus 1 is 0. Negative 1 to the 0 is 1. Positive 1, so you get the positive there. If I plug in n equals 2, 2 minus 1 is 1. Now I get negative 1 to the 1. That's negative 1, and I get my negative. And you can see that it'll carry out the rest of the way through. That is your Maclaurin series for sine of x. I already have that waiting for us in Desmos. So let's take a look at that now. Here is sine of x. Let me make sure. Let's bring our a value down. Sine of x looks like our typical sine of x. Here, and here I have n plus 1. It could be n minus 1. All we want to do is just shift it, so that way on odd terms, on even terms it's positive, and on odd terms it's negative. So that's fine. So I'm going to turn the function on, and so the first term of the series, again, bad approximation, does not look good. So let's now add a term to the series. Better. So around this area, it looks like the tangent line that goes through 0. Well, not quite the tangent because it's crossing over to the other side, but it pretty well lines up with this region right here. But now we want to start to curve, but the curving will happen with the increasing powers of x, because now we're going to have a polynomial, or a quadratic specifically, when we do the a equal to 2. So n equal to 2, let's look back here. N equal to 2. Actually, that's the third term. So we're already at, we happen to be at x to the 5th already. And we'll keep going. And again, you'll see that by the time I get to the 14th term, like we talked about with the exponential, you can't tell the difference between those two graphs. It's pretty cool to see. All right. Now let's do cosine. But instead of using our definition of Maclaurin series, let's use the understanding that the derivative of sine is cosine. So what that means, I should be able to take the derivative of the Maclaurin series for sine and get the Maclaurin series for cosine. So let's try that out. So I'm going to write that cosine of x equals, and we're going to come back up here and we're going to take the derivative of the Maclaurin series. So the derivative of x is 1. The derivative of minus x cubed over 3 factorial. Well, I bring the power down, 3. I subtract 1 from the power, 2. And the constant just comes along for the ride. Then I get 5x to the 4th over 5 factorial minus 7x to the 6th over 7 factorial plus and so on. But we're going to actually simplify this even further so we get a better pattern here. 3 factorial is 3 times 2 times 1. So this 3 that's on the bottom can cancel with this 3 on top, and 2 times 1 can be rewritten as 2 factorial. So this is actually 1 over x squared over 2 factorial. Let's see if that works for the other cases. 5 factorial equals 5 times 4 times 3 times 2 times 1. This 5 will cancel with this 5. And what I'm left with then is 4 times 3 times 2 times 1, which is 4 factorial. So we get a much nicer pattern because now the exponent will agree with the factorial terms. And we can make a prediction here. This will be x to the 6th over 6 factorial, and so on. So you can see now cosine only makes use of even powers of x, whereas sine made use of odd powers of x. That's one of the reasons why sine is referred to as an odd function and cosine is an even function. But let's simplify cosine down to its summation notation. This time I'm going to have an x to the power 0, so I'll include the 0th term. We want even powers. So the way we make even powers now is get rid of this 1 and just use 2n. So you get x to the 2n over 2n factorial. And now we want to alternate the sign still. So, but now just realize that I've shifted the series to start at 0. So we want that first term to be positive. So if I just include n, I can plug in 0, negative 1 to the 0 power is 1, and so that should do it for me. So there is your Maclaurin series for cosine. So going back to Desmos, take a look at cosine here. There's our cosine term. Here is our Maclaurin series. And if we add terms, we can see we build up cosine in the very similar way. By the time you get to 14 terms, you're very close to being exact within this range that I have listed here. The last thing I want to talk about is combining some of these ideas to prove Eulers identity, which is, to a mathematician, one of the most profound things that they have in their arsenal. So we want to bring up the concept of the imaginary number. That's supposed to be a straight axis. Let's try that again. Not much better, but we'll go with that. And we have the real axis here, the imaginary axis. You'll remember this from our discussion in the first video I had you guys watch before school started. And so this point here represents an imaginary number. It can be determined either by 2 points, A, B, or by finding the distance away from the origin and an angle theta. So we can write that Z equals A plus IB, or we can determine what A is using R and theta, and we can say that A is R cosine theta and B is R sine theta. Well, what we're going to do next is substitute in. I'm going to actually factor out R. We're going to substitute in the Maclaurin series for cosine and sine. Since we have just derived those, we can just copy them from our previous page. So cosine, that's our even function, is going to look something like 1 minus x squared over 2 factorial plus x to the 4th over let me keep the same variables. I'm using theta now instead of x, so it's going to be theta squared over 2 factorial plus theta to the 4th over 4 factorial minus dot dot dot. Don't have to write the rest of the series to know what those terms are going to be. Then I'm going to have plus I, and then in for sine we have all the odd powers. So we start with theta, and then we're going to have minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus dot dot dot. And so there we have what looks like a mess. But what I'm going to do now is we are going to, first we need to distribute this I to all these terms. And then I want to rearrange all these terms, mix them all around, and get them in order by the power of x, or in this case power of theta. So best explained this way. So it's R. So the lowest power would be theta to the 0. So that's just our 1. Then theta to the 1, that's going to be over here, but remember we distribute the I, so we're going to get plus I theta. Then it's theta to the power 2, so I'm going to get a minus theta squared over 2 factorial. Then the theta cubed is over here, but I'm going to have an I term, and it's also minus, so minus I theta cubed over 3 factorial. Keep going, plus theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial minus dot dot dot, and it keeps going. Well, I want to know if there's any series that looks like this. This looks like a McClaurin series. And there's one that is similar to this, but it's definitely not exact, and that's the exponential. The exponential starts with 1, and it's 1 plus, it would be 1 plus theta squared over 2 factorial plus theta cubed over 3 factorial plus theta to the 4th over 4 factorial. So the big differences here are that there are i's, and that they switch signs every second term. So it's like, you have 2 pluses, 2 minuses, 2 pluses, then it'll be 2 minuses. So, left to your own devices, it might take you a while to guess the right function for this. But if you stick with the idea that this looks very similar to an exponential and that there are i's in here, that maybe we can put the I in somewhere and create a function like this, f at x equals e to the I theta. Let me change this then. I'm switching back and forth from x and theta. So this is f theta now. F of theta equals e to the I theta. So why I might have some confidence with this function is because when I start taking derivatives, it's easy to take derivatives of the exponential. You get the same thing back, but with the I that we put out in the top, after taking its derivative, it comes out front using chain rule. So that you take the derivative of I theta and you get I, for instance. So the I gets multiplied out front. Well, every second term, you'll keep adding i's there. So it'll be I squared, I cubed. Well, I squared is -1. So you get rid of the I and you get a negative instead. That's what's happening here. We get rid of the I and we get a negative instead. So I'm feeling pretty confident that we've got something here, but let's actually test this out. So we'll do f prime of theta is I e to the I theta. F double prime at theta is, you bring another I down, you get I squared e to the I theta, which can be rewritten as this is -1, so it's minus e to the I theta. Third derivative, now it's minus I e to the I theta. And then to the fourth derivative, you get minus I squared e to the I theta. And that is, you get a -1 times -1, and you get +1. So you get e to the I theta. So just like sine, it repeats after the fourth derivative. So it takes 4 derivatives to do that, but it finally repeats itself. And what we see is that some of these terms will have i's in it and some of them have negatives in it. So that, again, gives me some confidence that we are onto something. Now, remember, the next thing that we're doing here is then we have to plug in, let me see the appropriate place for me to put this. We're going to plug in theta equal to 0. So we're going to evaluate all of these at theta equals 0. So what I might just do here is I'm going to write it over here. Theta f at 0 equals e to the 0, that's 1. F prime at 0 equals I e to the 0, that's I. Second derivative, evaluated at 0, I get a -1. Third derivative, I get a -I. Fourth derivative, I get 1. So there's our pattern. 1, I, -1, -I, 1, I, -1, -I, and so on. So let's write, if we write out the series of e to the I theta, it's f at 0 plus f prime at 0 times x, or in this case theta, so it's I theta, plus f double prime at 0, that's -1, times theta squared over 2 factorial, plus the third derivative evaluated at 0, that's minus I. You get theta cubed over 3 factorial. Fourth derivative is, you got +1. And you get theta to the fourth over 4 factorial. And you start to get the pattern. You're going to have plus I theta to the fifth over 5 factorial, and you're going to have a minus dot dot dot. Let's look above and see if what we have. We got a 1, 1. I theta minus theta squared 2 over 2 factorial minus, and so you keep looking and you find that that is the function we were looking for. So this piece right here equals e to the I theta. So that means I could, instead of using sines and cosines, I can use z equal to r, this r here, e to the I theta. So it's very, very strange because I mean, you can write cosine or sine using exponentials. We automatically know that sine and cosine are sinusoidal. They're functions that repeat. They're cyclical. But so is e to the I theta. E to the theta, the exponential is not cyclical. That just dies down. You know, it either grows or decays very quickly. But e to the I theta is a cyclical function. It repeats itself. It goes, you know, it's another way for physicists to represent oscillations. So to get Euler's famous identity, we want to substitute in r equal to 1 and theta equal to pi. Now, if I do that with this, that doesn't give me anything so significant because I don't know what that equals. I get z equals 1 e to the I times pi. But I don't know what the quantity e to the I pi actually equals. That's the one thing that sort of stumped people. That doesn't really have a definition. But again, it does have a value. And what you can do is use this form of the complex number and say that z equals, and we substitute in r equal to 1 and theta equal to pi, and we get that r is 1, and then we get cosine of pi plus I sine of pi. Cosine of pi is negative 1, and sine of pi is 0. So anything times 0 is 0, and so you get that z equals negative 1, and there we have the famous rule that e to the I pi equals z, which in this case is negative 1. So the exponential, the imaginary number, pi from geometry, the real numbers, it's a marriage of vastly different areas within mathematics, all combined together in a very neat and simple statement. That is Euler's identity, and it is something that is very often used in very advanced applications of quantum mechanics and engineering, and certainly for math, it's one of the most fundamental statements that they have in their arsenal. So I hope you enjoyed that, and we'll see you next time.